Another piece of information that we might want to learn is how much of the reactant is left after a certain amount of time has passed. If the rate remains constant, we can figure that out pretty easily. But that's only true for zero-order reactions. For first or second-order reactions, the reaction rate changes constantly with time because the reactant concentration is changing constantly with time. So in order to calculate the amount of reactant remaining after a certain amount of time has passed, we need a way to account for the changing rate. If we could really zoom in close enough and take a small enough slice of time, concentration doesn't change a whole lot from one moment to the next, so neither does the reaction rate. So this is where we might start to build a mathematical model. If we start from what we know, that the reaction rate is equal to the negative change in the concentration of A per unit time, and the rate is also equal to some proportionality constant K times the concentration A, then we can rewrite that to put everything about the amount on one side and time on the other. This sets us up to do mathematically what we're not able to do practically. The theory lets us find out how much reactant is used for each minuscule step forward in time. We solve this type of equation by integration, summing up all the area under the curve between our starting time and the time we're interested in. That means we integrate amount from the initial amount, or A naught, to the amount at time t, and we integrate time from 0 to time t, and that is equal to ln A minus ln A naught equals negative k times time, which is the relationship that we were looking for. It lets us enter an amount of material that we started with, the amount of time that has passed, and it tells us how much material is left. Let's explore some of the things we can do with this. First, in the linear form, which matches y equals the slope times x plus the y-intercept b, this tells us that if we plot ln A on the y-axis and time on the x-axis, then the amount at time equals 0 is the amount that we started with, which makes sense, and the amount lost over time is driven by the rate constant k, which shows up here as a negative slope. This linearity is a theoretical result, but one that can tell us whether our experimental data are first order. If the experimental reaction is a first order reaction, then when we plot the data as ln of concentration per time, it will be linear. Other orders of reaction will not be linear in terms of ln A per time. If we do some more work with the equation analytically, then we can generalize it to ask what fraction of the starting material is left. First, we'll put the negative onto the amount side, and so we switch these two terms, and then we use the fact that the difference of logarithms is equal to the quotient of logarithms to find a fraction of our starting material per material at time t. Now we can check to see how much time it would take to react 10% or 99% or anywhere in between. So let's try 50%. And what we end up with is finding that the time it takes for half of the reactant to go through the reaction is ln 2 over k, which is a really interesting result because we've canceled out the amount entirely. It doesn't matter whether we're talking about a mole or a gram or a ton. The time it takes to expend a given portion of the starting material in a first-order reaction is a constant. That means that if you start with 100 moles of reactant, it will take ln 2 over k time to have 50 moles remaining. And at that time, when you have 50 moles remaining, it will take another ln 2 over k to reach 25 moles, and another ln 2 over k to get 12.5 moles, and so on. Because the time it takes to remove half of the remaining product is a constant, we give it the special name of the half-life. At this point, you might be wondering how many half-lives it'll take to get to 0, to use all of the reactant. So, in theory, it will take forever for any first-order reaction to go to completion. We know that at some point before infinity time, the last molecule is going to react. And that's because we know that this reaction is actually discrete. The reaction steps through each full molecule and isn't really a continuous function. But at the same time, there are so many molecules, and each discrete step is so small that in truth we're completely justified to simplify our model as a smooth, continuous function. We just have to keep in mind that this model is going to break down near the limits. Theory-based analysis is a powerful and useful tool, but we must always remember that a model is only as good as the assumptions that go into it, and to explicitly state which approximations of reality we are willing to accept.